Welcome. In this session in linear data analysis, we'll explore the use of a different activation function for an artificial neuron. That is, we won't use the simple Heaviside quantization that we used for a perceptron. The need for this complexity is, let's consider a single neuron with linear activation. What that does is it performs a weighted linear sum of the inputs. Now suppose that we have a layer of linear neurons. That is, we have some neurons and these are computing linear sums, and then we're feeding them into something that computes a linear sum. Well, we can very quickly work out using some elementary linear algebra that if we take two weighted linear sums and we add them together, what we have is a linear sum. So if we continue to use linear activation, we're not going to be able to represent anything with a multi-layer network that we can't represent with a single neuron. So that means that we have to add nonlinearity somewhere. A problem is if we use Heaviside functions, the step functions, as the nonlinearities, we have a terrible time in propagating the label information backwards from the output through the hidden layers. So let's explore briefly what we mean by linear units produce a linear output. Here, what we have are the data, and then the data flow through one layer of neurons, and then they go to another layer. So if this layer of neurons is performing weighted sums, and that is their activation, and then if this neuron is performing a weighted sum and an activation, then even when we add a bias term, the weighted sum of two weighted sums is ultimately a weighted sum of these two inputs, x1 and x2. So if our network has all linear responses, then there's no way that we can get beyond this difficulty of there are certain things that it just can't recognize. So what Rummelhart et al. Suggested in their 1985 work, which is quite long, and their 1986 work, which was terser but more widely read, is they said, let's try adding nonlinear activations. So what this means is we begin with the data, and now we'll go through a nonlinearity, and if we recall what the logistic function looks like, it looks like a sigmoid or an S shape. So we could add a sigmoid activation to this neuron and a sigmoid activation to this neuron, and now when we perform the sum, it's not the sum of sums, it's the sum of a nonlinear activation of that sum, and then this is a nonlinear activation of this sum, and what comes into this neuron is already nonlinearized, and then we can further nonlinearize it. And on page 9 of their long technical report, they say we have used the logistic activation function. So let's now explore what they mean by that. By nonlinear or logistic activation, what we mean is that it will be a sigmoid curve. So the logistic activation looks like this. If this is the score of our data, then it will look something like this. And so what we have is we say that the score, the activation for an augmented data vector I, we earlier defined that as being 1 over 1 plus the exponential of the negative of the dot product between that augmented vector and the augmented weight vector for the neuron. So this, we can also see, is a smooth approximation to the Heaviside function. So the Heaviside function would do this. And the logistic function is smooth. And an important part is that it is differentiable. And because we can differentiate it, that implies, let's put an exclamation part because that's important, it's differentiable, and then the derivatives, so the derivative of the augmented weight vector approaches 0, as the score approaches plus or minus infinity. That is, we can see from this logistic function that as the score gets, say, strongly negative, this asymptotically, it becomes really flat, and really flat means the derivative is 0, and this means really flat. And what that implies for learning is that if we try to learn the data and we're working with derivatives, what that means is that we'll gradually disregard data that are strongly negative. That is, if they're really, really far away from the hyperplane, they won't have a lot of effect if they're on the negative side. And likewise, they won't have a lot of effect if they're on the positive side. So that is the basic idea. The trouble is that, to date, there is no known closed form. No closed form solution. And what that means is that if we are trying to learn this augmented weight vector and we're given a lot of data, there's no known way to simply compute it. With the perceptron, there is a known way, and the perceptron algorithm is guaranteed to converge. We don't know any way to find the weight vector, the augmented weight vector for a neuron that has a logistic activation in using any form of any closed form solution or any guaranteed iterative solution. So what this does is this is a bridge to other areas. So this would take us to nonlinear data analysis. And it also takes us to neural networks. And the neural networks are layers of these artificial neurons that have nonlinear activation functions. And it also takes us into statistics. And in statistics, it specifically takes us to logistic regression. And logistic regression and finding the augmented weight vector for an artificial neuron with this activation function are very closely related. So the basic concept, let's consider the residual error. And by that I mean of classification. So when I say the residual error, I mean the difference between the label and the output of the neuron. So Rummelhart et al., they use the squared error, and that's a term that we've used in many sessions. That, for example, is how we solve linear regression, is we minimize the squared error. In logistic regression, they use a different concept, and what they use is what's often referred to as the negative logarithm. And we won't go into either of these in logarithm. We won't go into either of these in extensive detail. We'll merely note for now that these are different approaches that can be used, and we'll try to visualize the results of using these different error methods.